Welcome to a lesson with Dr. Powell. Let's take a look at why, um, just by looking at the derivative matrix, we can actually detect that the curl is equal to zero. Um, well, let's take a look at the general case when we have a real part and an imaginary part for a function. So we write our function as a u plus iv. This is the real part of the function, the imaginary part of the function. And we're trying to integrate this. So we're multiplying by dx plus I dy. All right. Now, when we do this, we end up getting, so let's see, for the real part, and well, actually, I'm just going to split this into real and imaginary part. The real part will come from here and here. And so we'll end up getting u dx, and then looks like it's going to be a I times I is minus, so a minus v dy. And the imaginary integral over here will end up being coming from this and the inside here. So let's see, so u dy and v dx. So v dx and plus u dy. Now, in order for the curl to be zero, let's see what needs to happen. So what's going to survive is the dy portion of this, but it's going to be out of order. So it's going to yield a negative u y, partial y. And I made it negative because I'm going to change the order to dx dy. And then I have the right order here with x, so vx dx dy. Now I can factor out the dx dy, and really what I have here is negative negative uy minus vx dx dy. Now, if we take a look at this, we would want this part, since in the real this is the real part of this, we want this to be zero, because you can only be zero if it's zero in both real and imaginary parts. So this must be equal to zero, which means in particular that uy has to be equal to negative vx. Okay, so let's look over here. In this case, what's going to survive is a vy dy dx, but that would be negative because it's in the wrong order. Right order over here with an x, so we'll put plus ux, and that'll be dx dy. Now we would want this part to be equal to zero as well for the curl to be zero. So this tells us precisely that ux is equal to vy. Now let's take a look at the derivative of this function uv, thought of as with a vector output in two components, thought of as a matrix. So first take a derivative with respect to partials with respect to x. That's a v, sorry. The outputs u and v going this way in the rows. And then we have uy, vy. So this is our derivative matrix right here. So we got our derivative matrix. Notice these equalities. Let's use them right now. So vy is equal to ux. So we could actually write this down as ux down the diagonal. Now going this way, let's see what we have. We have uy is equal to negative vx. So we could write this vx as negative uy, or this uy as negative vx. We could do that. Negative vx, and we have vx. So this is our matrix. Now let's kind of see what happens when we take this matrix and we multiply by it. Here, if we multiply a complex number by it. Now, notice that complex number will serve as a run, and this will compute the rise, at least approximately, and it's an approximation is good nearby. So let's see if we have an AB, this is kind of like an A plus BI, and see what happens when we multiply it by this matrix here. Okay. So we end up getting across the top, we end up, and so let me just erase this to just have a little bit more room to write out what's happening here. Okay, so across the top we have, let's see, we have, so UX times A minus VXB. And then on the bottom, okay, so I'll just kind of do it like this, all right? So this is what happens from doing that and that. That's like the first component. The next component would be like VXA plus UXB. So quite literally, you could think of this as being, this is the real part plus I VXA plus UXB, just like that. Okay, so the result is that, so what we'd like to check to see is this result the same? I mean, do we get this same thing by is there a complex number that we can use that would get the exact same thing if we multiplied by it as this? If we multiplied it to A plus BI, would we end up getting this? So let's go ahead and look at that. And when we do so, we notice that UX plus IVX actually does the job. You can try this out. The imaginary part looks good here. That's exactly what we get. And for the real part, so UXA and VX, yep, it works out. So really, we get this, which is kind of amazing, that the derivative here of this actually just ended up being this right here. Kind of fancy that we just got a complex number acting as its derivative. So now a complex number acting as its derivative right here kind of comes, how did that come to be? Well, that came from the equalities that we got where we in here. And those equalities that we got came from the fact that we were assuming that the curl was 0. So if the curl is 0, then we end up getting that it's acting like a complex number. Now, if it's acting like a complex number, it actually has to take this form as well, which actually forces the same equalities, which makes the curl 0. So it's actually an if and only if kind of criterion. And it's kind of nice. These are called the equations that we just related right here to make this work are called the Cauchy-Riemann equations, abbreviated CR perhaps, and they ensure that the derivative will exist and that you'll have a potential function even, and that your line integrals will be the same if you go this way or that way. So kind of you get a lot of things off of those, and they're just two very simple equations which we had from here, where this is equal to 0, which meant that we needed to have that uy was equal to negative vx. We also had to have that ux is equal to vy. So we have these basic two equations here where we're looking at the real and imaginary parts of a function. And if we have that going on for a complex valued function, then for sure we're going to have these nice criterions, these nice ideas that we just discussed. Thanks for watching.